SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the course Applied Thermodynamics, Module 6, Reciprocating Air Compressors. There are two lectures on this module. First one is reciprocating compressor, mostly in the single stage compressor, its analysis and modeling, which we have covered. And in today's lecture, we will be discussing about multi-stage compressions, how you are going to do its analysis and modeling. Now, under this multi-stage compressions, and before you go for this multi-stage compression mode, we also have to know some certain basic concepts for the compressor and what we call as a clearance volume and volumetric efficiency. And in fact, these two things are very much required when you deal with the multi-compression mode, maybe involving number of stages. Then we will try to see what is the modeling for this multi-stage compressions, and finally, I will end this topic by through a thermodynamic steady state analysis for a two-stage compression. Now, in the last lecture, that is when you dealt with the single stage compression. So, what was the main intention is that we have piston and that piston moves in a cylinder, and in fact, there is zero clearance. That means, it is assumed that piston position is just end of this cylinder face, and where this induction or inlet or exit valves are placed. So, through this induction the air enters into the system or into compressors, and through delivery finally the pressure that goes out is at higher pressure P2. So, the very basic bottom line is that at the end of our compression process, the gas undergoes a pressure change from P1 to P2 by following a thermodynamic compression process, polytropic process, that is Pb to the power n is equal to constants. And for this compression process, we derived that how much indicated power is we require. And this indicated power is expressed in many versions. One is in the form of temperature ratios, other is in the form of pressure ratios, and where in some cases we have used mass flow rate, in some cases we have used volume flow rate. So, this is how and depending on the nature of the problem, we can use this expression. Another important aspect is that an ideal compressor would be the one which consumes minimum work, and this minimum work we have seen that from this curve we have seen there are two extremes. That means, if a compression process goes from A to B, which is a normal process, and that follows the law of Pv to the power n is equal to constant, and we have seen is that the only possibilities that we can minimize the work is only through the index, by changing the index of compressions, because P1 and P2 is desired by the user, volume is fixed by the given size of the compressors. So, only possibilities to minimize the work is based on the value of n. And what we can see is that if you look at this value of n, ideally if you in particular if you take isothermal process, your n is equal to 1, we saw is a so this equation becomes Pb is equal to constant, and when n is equal to k or gamma, that is for air, that value is 1.4. So, the other extreme is the Pb to the power gamma or k is equal to constant. So, in that sense that we can think of a two extreme processes, one is isothermal process AB1, other is the isentropic process AB2, and through these processes we can say that isothermal process undergoes the minimal work, because from the area under PV diagram we will show you that isothermal process will give you the minimum work, whereas the isentropic process will give you the highest work. So, isentropic process is not advisable, and isothermal process is, although it is goes for minimum work, and it is not a realistic version, because when you do this compression temperature is going to increase, and it is very difficult to maintain a constant temperature isothermal process while undergoing the compressions. So, ideal nature of this compression process is normally dealt with Pb to the power n is equal to constant, and typically n value is kept in the range of 1.2 to 1.3. And based on this isothermal compressions, we can find the ratio that what is the isothermal efficiency, that is minimum work for the isothermal process to the indicated work. Next thing is that we are going to dig into this another concept, which is clearance volume. So, it is a realistic version of a single stage compression process. A realistic version can be realized only when we can have a clearance volume to be maintained in a piston cylinder arrangement. That is mainly because since all of them, the piston is a mechanical device and it has a finite length of travel, and we call this within the cylinder, and we call this as a swept volume. There are the upper limit and lower limit, and at the same time we also expect that piston should not go and hit the bottom part of this cylinder. So, for that thing that we must expect that there has to be a clearance volume and for the free movement of the piston within the cylinder. And also there will be also water jackets in and around that there, because what we see is that we have to keep this temperature to be close to isothermal, so that during the compression process we can take out this heat through the water jackets. So, that is the reason that we expect that two things. One is we have to more or less find a realistic version to maintain close to isothermal process just by releasing the temperature of heat from to the water jacket. Second thing, we have to maintain a clearance volume, and typically this for a good quality of compressors, the minimum recommended clearance is about 6%, but it can go up to 30 to 35% maybe for a large scale. But when the delivery stroke is completed, the clearance volume is completely filled with the gas P2 and T2, and during the piston movement of subsequent motion in the induction stroke, the gas expands behind it till the final pressure is reached. What it means is that when after the compression process that starts from A and goes up to B, and thereby this delivery of air that goes out, but side by side there are some gas that left out within this clearance volume, and during the piston's backward movement these gases tries to expand. So, when they expand, the volume which was supposed to be at C now expands, and finally the pressure comes down to P1, and from this your actual volume that gets induced, that is from D to A, that is the amount of gas that is required for this volume, that is V A minus V D. Now, what happens is that by introducing this clearance, so ideally this, if there is no clearance, it would have started taken this volume, swept volume as V S, and since there is the gas expands, so the induced volume gets reduced, that is from original value V S to V A minus V D. So, that is the effect of clearance. So, the induction of fresh charge begins as soon as the initial pressure is released, and it continues till the end of the point A for the induction stroke. So, gas is then compressed by obeying the polytropic compressions, and delivery of gas begins from the point B. The effect of clearance is to reduce the induced volume at point P1 and T1 to that is from V S to V A minus V D. Another interesting point is that when you actually see this compression things, that whatever mass that is available at point A, m dot A, and that that entire mass gets compressed, so it becomes m dot b. So, m dot A is equal to m dot b, and what are the left out gas, that is at point C, m dot C is equal to m dot d, because this gas actually expands, and due to this presence of the gas, your induced volume into the cylinder gets reduced. But at end of the day, what happens, if you take the final thermodynamic states from 1 and 2, you will find that m dot A in the forward cycle, m dot A is equal to m dot b, in the backward cycle m dot C is equal to m dot d, at the end the pressure rises from P1 to P2. So, initial pressure P1, now final pressure P2. Now, let us see some mathematical insights, what happens if there is a clearance volume, what happens to our indicated power calculations. So, first thing we have to calculate the mass of the gas at important points A, B, C, D, and we have already proved that m dot A is equal to m dot b and m dot C is equal to m dot d. So, this mass delivered per unit time will be m dot b minus m dot C, and that is equal to m dot A minus m dot d. So, that is m dot. So, m dot is the mass that is actually delivered per unit time. And now, from this PV diagram, we can easily calculate what is the value of indicated work, and that is nothing but your area A, B, C, D. And this area is nothing but the difference in the area, that is A, B, E, F minus area C, E, F, D. So, if you take these things, then if you recall our earlier expressions, the indicated power can be calculated by two expressions, these two, and that follows this, for that is required for these areas, and ultimately since m dot A minus m dot D is equal to m dot. So, you can rewrite this expression as indicated power is this. So, this comparison for earlier mathematical expression for single stage compression without clearance volume, we have also same expression. So, this means clearance has no impact on the indicated power, but what it does, it changes the volumetric efficiency, which will come later. Then other expressions for these things we can write is that in same way, that I p in the form of volume, flow rate, and if there are f number of cycles per unit time, this volume will be f into B A minus B D, that is the actual volume, stored volume that enters into the cylinder. So, this is how you are going to recalculate our indicated power if there is a clearance volume present in the compressor. Thus, what conclusion that we can derive, that the work done in compressing the mass of the gas at C or D through this compression process A B is returned when the gas expands from the C to D. So, the work done per unit mass delivered is unaffected by the size of the clearance volume. But what happens is that since there is a limitation of mass that is going to be inducted, this mass delivered per unit time can be increased by designing the machine to be double acting. So, the other way of looking at the same problem is that we can say that it is single stage compression, but double acting. Double acting basically means that if it is a compression stroke, during compression stroke, other side would be other one would be a expansion, and vice versa. So, basically speaking, that if there are the inductions and delivery valves are arranged in such a manner, when the piston gets compressed, so this part of the gas gets compressed and the other part of the gas gets expanded, or it is a delivery. So, this gas, this is a delivery part. So, when it is for this compression stroke, this is the delivery, and vice versa, and when the piston moves backward, the bottom part of the gas gets compressed and top part of the gas gets expanded. In a sense that for same movement of the pistons, we can get a double mass flow rate for a with some change, some bare minimum change in the arrangement. So, that particular machine we call is a double acting machine. The another version of the indicator diagram, what we also call as actual indicator diagram. So, what we have seen is that either induction or delivery of air, we have the inlet valve or delivery valves. So, these valves are like a cam operated valve. So, cam operated valve means they suddenly opens and suddenly closes. So, this type of things although they are automated, but these types of opening, continuous opening and closing leads to some kind of waviness in the indicator diagrams. So, if you look at the actual PV diagram, which is constitutes A, B, C, D, and this is how we did our analysis. And if you look at these things, but what may happen, there will be some waviness in the cycle, and mainly during this not in the compression and delivery part, but only during the suction part and the delivery part. So, during compression and expansion we will see this waviness is not there. So, that thing we call this as a actual indicator diagram. And also another important aspect is that during the induction process, which is nothing but a mixing process. So, that means during the induction stroke and the gas which was at point C, now that gas has expanded and at point D. So, we have this is as a existing gas, that is at m dot D, and this is the fresh gas that during the suction stroke that enters into this cylinder, and this gas comes from the clearance volume. So, these two gas mixes. So, this induction stroke is now another mixing process, and this mixing process also has some boost for this kind of waviness on the indicator diagram curves. So, let us talk about another terminology what we call as a volumetric efficiency. So, what we have seen is that indicated power remains same irrespective, because you are by putting the clearance. Then the question will arise that you can then there is no limit for the clearance. Other parameter that happens is that volumetric efficiency. Now, if you want to have a larger volume to be handled by the same compressors, then although we may not have a significant contribution of input power in indicated power requirement, but you have to compromise on the volumetric efficiency or volume handled by the compressors. So, that is the how do you quantify this volumetric efficiency and what are the significance, and all these things we are going to discuss here. So, the one of the major effect of clearance is to reduce the induced volume to a value less than that of swept volume, that we can see that initially this volume was Vs, now this volume becomes Bm minus Bd. So, this Vs is now reduced to Bm minus Bd. So, see the cylinder size increases for a required induction over a value and calculated under 0 clearance. So, if that is as to this is the case, then cylinder size must increase. Another important aspect that we frequently use the term what is a FAD. So, what is called as free air delivery, and that is for an air compressor we say is that volume of air per unit time, that we call this as a FAD for a compressor. So, it is the rate of the volume delivered from the compressor, and it is measured at pressure and temperature in which compressor is installed. So, what happens is that the mass, you can see that there will be the suction pressure may be different, but the volume that the air that comes in which, see what happens is that when the compressor is placed in atmospheric conditions, so atmospheric air enters. Now, for air to enter into the system, we must create a pressure difference. So, normally the suction pressure for the compressor is kept lower than the atmospheric. So, the suction pressure is different from the atmospheric pressure, but the gas that enters into the system, it is atmospheric. So, all this mass flow rate which was calculated is based on the atmospheric conditions. So, that is what it says, that the free air delivery is the rate of the volume delivered from the compressor, and this free air delivery is measured at pressure and temperature in which compressor is installed, and typically it is atmospheric pressure and temperature. And now to quantify this clearance volume, we define a term what we call as a volumetric efficiency. In fact, there are two definitions, one is in the form of mass, other is in the form of volume. So, the volumetric efficiency is ratio of the volume of the gas delivered, and what is that volume? This volume is measured at free air pressure and temperature to the swept volume of the cylinder. So, cylinder swept volume is fixed, and the volume of the gas that is delivered into the system, that is measured at free air pressure and temperature, that is FAD. That is one expressions, and other expression, that means m dot v volumetric efficiency is equal to V by Vs. The other expression we can also use, that volumetric efficiency is the ratio of mass of gas delivered to the mass of gas that would fill the swept volume at free air conditions of pressure and temperatures. So, that means another expression we say delta V is equal to m by ms. Now, we can see that both the expressions are identical. How? So, if you talk about this mass we can calculate PV by RT, and ms, that is swept volume, which corresponding to P into Vs, that is swept mass is equal to P into Vs by R into T. And here there are two things, one we have V. So, V is nothing but the free air delivery, that is measured at pressure P and T, and the Vs is the swept volume, that is measured at pressure P and T. Now, if you can take this from the definition, if you take eta V by is equal to m by ms, and from this equation we can find that volumetric efficiency in the function of mass ratio and as well as the volume ratio with respect to actual volume, with respect to swept volume, and with respect to actual mass with respect to swept volume mass. Now, let us find out more details into this mathematics. Based on this indicator diagram, we can derive some working formula. And what is that working formula? How much volume which gets induced? If I say that is Vi, that is nothing but Va minus Vd. So, this Va is nothing but your Vc plus Vs, which is mentioned here, minus Vd. Okay. And but we know that Vd by Vc is equal to P2 by P1 to the power 1 by n. So, that is the index of compression. This equation holds good, and from this we can simplify this expression, that means induced volume now becomes Vs minus Vc entire multiplied by P2 by P1 to the power 1 by n minus 1. So, from this so by definition this volumetric efficiency we can write Vi divided by Vs. So, from this expression we can write this one as, we can find a volumetric efficiency expressions, and in the form of clearance volume Vc, swept volume Vs, and pressure ratio P2 by P1. Of course, there is a index of compression n is there. So, here this free air delivery, okay. Another point is that in reality the gas will be heated by the cylinder 1, and there will be reduction in the pressure due to the pressure drop to induce the gas into the cylinder against the resistance of the flow. So, what happens is that when you calculate this mass flow rate, and that mass flow rate, whatever actual mass flow rate Pv by RT, and your volume is nothing but your Va minus Vd. Okay. But this the mass that the volume that here this V or this Vi, whatever calculation that we are going to use, which is volume induced, that is Vi is equal to Va minus Vd. But if such a case happens that your suction and your atmospheric conditions, they are different, and that is when that happens, your this Va minus Vd will be now replaced with T by T1 into P1 by P, because this equation holds good. That is mass flow rate remains same, that is Pv is equal to RT, and that is also equal to P1 into Va minus Vd by RT1. So, 1 stands for the initial state in which the air is available to us. Okay. So, this is all about clearance volume and the volumetric efficiency. Now, let us see now use this particular concept, that how you are moving for a multi-stage compressions. So, what we have already seen is that we have a condition of minimum work in a compression process, for which the compression has to be isothermal, but delivery temperature increases with the pressure ratio. So, maintaining an isothermal condition is a difficult task, side by side increase by through this compression process. But at the same time, if we increase in the pressure ratio, there is a decrease in the volumetric efficiency. So, these two things has to be compromised, and the effect of clearance volume to reduce the induced volume of the gas. So, therefore, for a required free air delivery, the cylinder size must be increased for higher pressure ratio. That means, if you want to go for a higher pressure ratio, so in a single stage compression it is not a viable option, and your cylinder size must increase. Now, when the cylinder size is increasing, that means we have to achieve this compression process. When you are doing this cylinder size increasing, then what happens? This swept volume drops, actual volume that enters into the system drops. So, if you can look at this particular cycle, so let us see that we are undergoing a compression from P1 to P2. So, when we are doing P1 to P2, then we can draw this cycle, actual cycle, that is cycle is A, B, C, D. So, free air delivery per cycle would be V A minus V D. Now, if you go to another compressor compression from P1 to P3, your FAD per cycle would be V A minus V dash, and if you go from P1 to P4, then it will be V A minus V double dash. So, what we have seen is that with zero clearance the volume was short volume. With increase in the pressure ratio, your free air delivery drops. So, if this drops, but we do not expect that free air delivery to drop. So, and also because of this pressure ratio, your volumetric efficiency also drops. So, because of this reason, we have to see that a single stage compression is not a viable option. So, we have to go for a multi-stage compression. Now, the most basic version of a multi-stage compression is a two-stage compression. So, two-stage compression which is shown here, that if you want to go for compression process from P1 to P2, so in a first stage compression we can go in a cycle A, B, C, D, but during this compression process what happens, your temperature also increases. So, the next stage compression has to start at a higher temperature. So, the cycle starts, the second stage higher compression starts at point A double dash, B double dash, C dash and D dash. So, what we can see is that we say is a LP stage, that means low pressure stage, and this particular we call this as a high pressure stage. So, in a two stage compressions we have two stage, a low pressure stage and high pressure stage. But what happens here is that your indicated power also shoots up because your temperature goes up. So, for that there is some kind of compromise that we have to do, that when we go for a stage multi-stage compressions, and moreover if your temperature goes up, your indicated power also becomes higher. So, we must do some kind of solution for this case. So, this very basic summary is that after the first stage compression, the fluid is passed into the smaller cylinder in which the gas is compressed to the required final pressure. So, in a two stage compression there is a third cylinder from which the induction process is initiated for the second stage compression. So, cylinders of successive stages are proportional to take the volume of the gas delivered to the previous stage. So, a typical version of two stage compression goes like this. What happens is that since if you look at this particular PV diagram, we have seen that actually this process, the LP stage is this one, bottom part, high pressure stage is the top part, and cycle in the high pressure stage is A double dash, B double dash, C dash and D dash. But what happens is that at point B temperature is high, and we do not expect that if you away from the point B, you can see that incurred area will be also higher. So, we will try to push this fellow B towards the left side, so that temperature comes down and the power requirement in the HP side should be less. So, for that the other possible alternative is that we add a intercooler. So, what an intercooler is that between a, so we have a LP first stage, that is low pressure stage, for which the cycle is A, B, C, D, and the second one is the high pressure side, HP side. So, the cycle is A dash, B dash, C dash and D dash. Now, in between we add a intercooler. So, what does this intercooler do? So, when you think a thermodynamic state at point the beginning stage, we have P1 and T1 stage, and after the first stage compression the peak pressure becomes Pi. Side by side your temperature also becomes Ti, also increase. We have also seen that delivery temperature also increases with the pressure ratio. But the problem is that this Ti is a higher temperature, and because of this reason, that means instead of the second stage compression actually starts, instead of B it will start from A dash, and since it starts from A dash, and if you continue A double dash and B double dash, C dash and D dash, then it will have higher area. So, what the entire objective is that we have to bring down the temperature of the gas through an intercooling arrangement. So, what does intercooling do? We have a circulating water, and this circulating water takes out heat from this gas. So, that with an intention is that with a complete intercooling, the whatever rise in the temperature that happens in the first stage, the entire gas is now with a pressure Pi, but at temperature T1. T1 is nothing but the way it has the gas that has entered, and the second stage again starts with a pressure, higher pressure, but with a lowest temperatures. So, the second stage compression, with second stage compression we get the desired pressure P2 and T2. So, this is the entire objective. So, that what intercooler does, this intercooler takes out this heat that from this gas, and through this process what benefit we get? So, instead of point B shifting toward A double dash, point B shifts toward A dash. So, as a result we can see the hashed area A dash, say double dash, B double dash and B dash, and this hashed area is nothing but your saving of work in the high pressure stage. So, this is the advantage of multi-stage thing, and because of this reason always multi-stage compressions is also integrated with an intercooling arrangement. So, if you look at this another version of temperature entropy diagram, what we have we have pressure P1, P2, and side by side we have intermediate temperature Ti is nothing but which is T2. And from these isentropic equations we can find out the intermediate temperatures, and of course, we can get the indicated power from that expression, and from this we will say that we will have a saving of work as n is the shaded area. Now, the question is that what is the ideal conditions of this intermediate pressure? Through an intercooling, so what happens that when the compression between the stages is undertaken without intercooling, the delivery process from the first stage or LP compression stage is at the same pressure and temperature of second stage or HP compression stage. But when an intercooler is incorporated between these stages, it is assumed that the gas is brought back to this inlet temperature after first or LP stage, but at the pressure same as that of first stage compressions. So, this is a case of perfect intercooling. Through this process, the second stage compression is performed with a gas at inlet temperature, but pressure with the first stage compressions. Now, the value of intermediate pressure has to be chosen in such a way that work, the indicated power requirement will be the minimum. So, for this case mathematically it is possible to obtain an expressions for minimum work for a two stage compression systems corresponding to the intermediate pressure. And but these things we also, this particular philosophy can be extended for the any number of stages. So, the conditions for minimum work is that the pressure ratio in each stage is same and intercooling is completed. So, the since there are two stages, the total indicated power we can calculate for the LP stage and for the HP stage, and individually for low pressure stage the pressure shoots from Pi to P1, and in the HP stage the pressure shoots from P2 between P2 and Pi. So, we say this is HP and this is LP, and this goes from P to P1 to Pi, and again from Pi to P2, that is LP, and this P1 to Pi is your LP stage, Pi to P2 is your HP stage. And this equation you can simplify in this form, and if you dig into little bit of mathematics into it. So, what we have is that this for a minimum for a fixed value of P1, T1 and P2, that means for a fixed inlet conditions P1 and T1 and fixed delivery pressure P2, that is the requirement. The condition for minimum power, we can write d of this indicated power with respect to Pi is equal to 0. So, these particular expressions in the bracket has to be differentiated with respect to Pi, and after this performing this mathematical differentiation, then what we land up having a very simple expressions, Pi square is equal to P1 into P2. So, it is a geometric mean. So, intermediate pressure is nothing but the geometric mean of P1 and P2. And there are other ways of rewriting that same expression in the form of Pi divided by P1, that is square root of P2 by P1. So, accordingly, if you do that, we can find that minimum indicated power for a perfect intercooling arrangement will be 2 times m dot r T1 n by n minus 1 to P2 by P1 to the power n by n minus 1 minus 1. Now, if there are z number of stages, then we can write this particular expression Pz by P1 is equal to P2 by P1 to the power 1 by z. So, accordingly we can rewrite these particular expressions, and so where z is the number of stages. Okay. The next part of our analysis is a steady flow analysis, and which we are going to deal with for a 2-stage compression systems. So, after dealing with the multi-stage compression, let us see that if we can do some kind of analysis, that analysis with main intention is that, so we have seen is that always this compressor is integrated with thermal circuits to take out the heat as much as possible. With a main intention is that we have to resemble this compression process close to isothermal nature to minimize the work. So, what happens, we can see that WL is the work which is gets added for a given mass flow rate of air at condition P1 T1. In the LP stage, heat and work is getting added, and finally from the LP stage when the gas goes out, same mass flow, but at different pressure Pi and Ti, then it goes to an intercooler, but intercooler there is no addition of work, rather there is a saving of work. But the pressure, there is no change in the pressure, so it is becomes Pi, but temperature drops to T1 again. So, T1 is nothing but the temperature at which it enters into the LP stage, and this is the one amount of work that has to be heat has to be rejected. But here the one and in the similarly for HP stage, we have also same there is a work transfer as well as heat transfer, and ultimately from P1 and T1 we as a user will get P2 T2 conditions. But here what has always this is a work transfer which is given as input, but in all the cases what we can see always there is a heat rejections. Of course, that is here it is heat is added into systems, but in reality the heat is getting rejected from the LP stage or intercooler or HP stage. Now, with this analysis we are going to quantify what are these heat losses that comes out from this LP stage, intercooler and QH. So, this is the entire motive of this steady flow analysis. So, in a 2-stage compressions we can apply these equations for intercooler and HP stage, and the actual power input always exceeds the minimum work input due to frictional resistance. So, we can say that about 50% of friction power goes towards the increase in the energy transfer to the cooling motor. So, this particular has to be a realistic estimate. So, this is although we say that your work requirement, but we also have to quantify the amount of heat that has to be taken out, because this the power requirement will be 50% higher than that, mainly due to the friction power and temperature rise. So, for that a simple steady flow analysis equations for LP stage, intercooler and HP stage carried out here. For LP stage we can see the energy balance equations, and ultimately we find the heat rejected from the LP stage is equal to Q dot L minus W dot L is the work input for this low pressure stage minus m dot Cp into Ti minus T1. And for the intercooler there is Qy, that is the heat rejected from this intercooler that goes out, and for similarly for HP stage we say heat rejected, because while deriving the expressions we have used this as a heat as input, but actually heat is getting rejected. So, we have written this that heat is rejected from the HP stage. And for this minimum work, when there is a minimum work, the low pressure stage and high pressure stage work transfer are equal, and that is what your PV diagram is designed, and so that we have this expression n by n minus 1 into m dot r into T2 minus T1. So, this is a very simple thermodynamic analysis through steady flow equations. So, with this we conclude this reciprocating compressors. So, whatever we have covered today, if I will just try to solve a simple problem based on our analysis or discussion today. The problem for discussion today is a two stage compression. So, if you incur or if you come across such a problem, first thing that we must do is you have to draw this thermodynamic PV diagram for a two stage compression systems. So, this diagram has basically three parts. One is pressure P1 at which gas enters, pressure P2 at which gas is delivered, and there is a intermediate pressure Pi, and this through clearance volume you can draw this first stage compression systems. So, we say it is A, B, C, D, and so B A minus B D is your volume induced into this cylinder. So, we have clearance volume, we have stroke volume, and in the second stage compressions, and since it is a intercooling things, so it has to start at some lower temperature. So, it is A dash and the compression goes A dash, B dash, C dash and D dash. Okay. So, our main target, we have to find out the indicated power first thing and sweat volume into the cylinder. Sweat volume into the cylinder, there are two parts, one is high pressure, other is low pressure. You have to calculate it separately, and this is to be happen for a given mass flow rate, that is 5 kg per minute, and the pressure ratio is 9.5 and the gas is at atmospheric conditions. So, there are some basic assumptions that we have to record first. So, induction compression we are assuming as 1.3, m dot is given as 5 kg per minute, and R, that is for air, is 287 joule per kg Kelvin. T1 we assume to be 25 degree centigrade, so or 298 Kelvin. P1 we say it is 1.013 bar, that is 1.013 into 10 to the power 5 Newton per meter square, and P2 is square root of 9.5 into P1. Pi is your square root of 9.5 into P1, that is intermediate pressure with a perfect intercooling. And P2 is 9.5 times P1. So, final pressure ratio is 9.5. So, first thing we have to find out this intermediate pressure Pi. Pi already we can note down from this, and this is 3.08 P1. Okay. First thing that we are going to calculate is indicated power. So, indicated power is equal to twice into n by n minus 1. Remember, it is a 2 stage into m dot r T2 minus T1. Understood? So, once we have said this, then all these numbers Ti minus T2. So, T2 or Ti would be Pi by P1 to the power 1 by n and into T1, n minus 1 by n into T1. So, that is the law of compression. So, we have T1 already, Pi by P1 we have already calculated 3.08. So, from this we can find out Ti as 385.9. So, putting this value we can write indicated power as twice into 1, n is 1.3 divided by 0.3, m dot r is 5 kg per minute, that is 5 by 60 kg per second, r is 287, Ti minus 1 is 385.9 minus 298. So, from this we can calculate indicated power as 18.22 kilowatt. Okay. Then we are going to calculate the swept volume. So, the swept volume has two parts. First is LP cylinder, and for this LP cylinder we can write this VA minus VD. We refer that indicated power m dot r T1 by P1, and here m dot we can write, because this is piston, the compressor is running at 320 revolution per minute. So, m dot is equal to 5 kg per minute divided by 320 revolution per cycle minute. So, this turns out to be 0.015 kg per cycle, and then we can write this induced volume 0.015 into R is 287, temperature is 298, pressure is your initial pressure 1.01325 into 10 to the power 5. So, this number is 0.0127 meter cube per cycle. So, we can now record this volumetric efficiency as 1 minus Bc by Bs into Pi by P1 to the power 1 by n minus 1. So, here Vc is your 6% of Bs. So, we can write this equation and find out the values, that is 1 minus 0.06 into Pi by P1 is 3.08 to the power 1 by 1.3 minus 1, that is 0.92. Our volumetric efficiency is now 92%. So once you this by definition of this volumetric efficiency, we can write V A minus V D divided by the V S, that is volumetric efficiency. So this will give you V A minus V D, and that is nothing but the swept volume. That will be swept volume Vs will be Va minus Vd divided by eta V. So, we will say Vs is 0.0138 meter cube per cycle. Similarly, we can find out this is for LP. So, repeat for HP stage with same expression, and this will imply Bs for HP stage will be equal to 0.0446 meter cube per cycle, and third part is the heat loss to the cooling water. So, there are three parts. We can write Q dot L is equal to W dot L minus M dot Cp or Ti minus T1. So, and this indicated power already we have found that W dot L is equal to W dot H, that is the assumption we said for minimum work, and total indicated power is 18.22 divided by 2. So, this that means W dot L is equal to W dot H, that is equal to 9.11 kilowatt. So, this equation we have to use here, sorry, W dot L you have to use here. M dot remains as 5 kg per minute, and Cp we know. So, we can write that 9.11 minus 5 by 60 into 1.005 Ti is T2. So, T that is 385.9 minus 298. So, this number would be 1.75 kilowatt. Then we can find QH, that is W dot H minus M dot Cp with same temperature difference, T2 minus T1, and this becomes 9.11 minus 5 by 60 into 1.005, 385.9 minus 298. So, this is also 1.75 kilowatt. Now, what remains is that what is the heat loss in the intercooler. Now, for this intercooler, the difference between these two is nothing but the intercooler heat. So, we can write Qi, that is for intercooler, is nothing but M dot Cp into Ti minus T1. 5 by 60, 1.005 Ti minus T1 is 385.9 minus 298. So, the answer here becomes 7.325 kilowatt. So, the answer that goes that heat loss to the cooling water jacket is for LP stage is 1.75 kilowatt, for high HP stage is 1.75 kilowatt, but the intercooler takes about 7.325 kilowatt of these things, and because of this reason we will have a saving in the work in the high pressure stage. Okay. With this I conclude this module, that is last module, module 6, reciprocating air compressors, and of course with this also I conclude this total lecture topic on the applied thermodynamics. With this I hope learners will get benefit out of this course. Thank you for your attentions. That is all for this course on applied thermodynamics.